So if you have used Blender assets before, you probably know it's pretty easy. You just drag and drop those, right? And for example, if I select this anvil looking fractal here, I'm going to drag this one here, and well, voila, here we have this, right? It's looking pretty, it's pretty detailed as the default fractal already. But that is how the pack works, you know. The numbers here mean that the 0 here is the bare bones version of the fractal. So for example, the Mandelbox formula, the clean formula, comes from this 00 Mandelbox, right? And the preset is Mandelbox 03. Another version of the Mandelbox is Mandelbox 04, for example, which looks like that. So, I mean, this is pretty self-explanatory. Just so you know that the first fractal machines are for the just ready for experimentation, and the other ones provide a starting point, or you can use them right away in your work. So this is how we drag those in, but this is not as simple as that, because here we have 4 or 3 options, right? We have link, append, and reuse data, right? This is regards to how the data of the object will be used by Blender. So for example, let's say I'm gonna drag in this Apollonian 03 fractal, and let's say I drag in another one. Now I set both to append, reuse data. So this means if I do something with one of those, for example, by opening up geometry nodes down here, I'm going to open up geometry nodes, and here we have this fractal node setup and some optimization, which we're going to talk about later on. So for example, if I change this one's iterations to 2, they both change to 2, and I mean, I cannot change them separately because they share the same data block. Now, if I don't want this to happen, what I should do is to select just append and drag in the Apollonian fractal like that. Now I can change the iterations however I please, and this doesn't affect the other instance. Or technically speaking, this is not an instance, this is just a whole different object, right? So this is how importing them goes. And the link here isn't highly useful in this case, because this is more like I imagine in a production pipeline when one artist creates an asset and it has to be the exact same location and no parameters changed, then you can use this one. But I mean, in our case, you do want to change the parameters. I mean, you even cannot move the asset around, right? It stays in the exact same location as it was in the reference file. So this is not useful for us right now. The difference between appending and reusing the data is also the fact that if you reuse the data, I mean, you reuse data, which means it's much less taxing on your hardware. You don't have to use as much VRAM, as much CPU power to load the scene and all this stuff. So just keep this in mind if you're using same objects. I mean, it's pretty wise to use the reuse data option. So this is about dragging those in. Now the question is, how do we change the parameters of the objects, right? So for example, if I drag in the Mandelbulb object here and put this here, then this looks like that. For example, let's say I want to change a parameter, I want to tweak, I want to see what is happening with it. And currently you see I cannot change the parameters, they're grayed out because I have linked this accidentally. But I'm gonna delete this and I'm gonna drag this into my scene again. Now, we have quite a lot of parameters here, and don't be afraid of those because they're actually very easily organized so that you don't have to like second guess anything. So the first parameters up until the scale of each fractal are fractal specific parameters, right? So for example, if I select another fractal like the Apollonian, this one also has parameters up until the scale, which are fractal specific. This one only has 3 fractal specific parameters, while the Mandelbulb 04 has or Mandelbulbs in general have seven different parameters you can change. So some fractals can be changed more than others, although I made my efforts to make all of those at least somewhat customizable. What do the parameters mean? Well, the fractal specific parameters are pretty math centered, most of those. But the ones that are important to know are the iterations, because the iterations define how detailed the mathematical surface of the fractal will be. And the stress is on the word mathematical because the visible detail might be different depending on your resolution. For example, if I change the resolution to be, let's say 20, you see we have way too little detail here to show all of the glory of the fractal. But if I put here, like, for example, 200, you see we have quite some more details. So I'm going to put this back to 100 for interactivity, and let's see what this does, right? So the first iteration, as you see, mathematically not a lot of complexity here. The second iteration adds more, and the third adds even more, and the fourth adds even more, and so on and so on. The next one is the normal Julia, normal/Julia. Mathematically, Julia sets is something much more wide than the fractal like area in general. This can be applied in other mathematical domains also, but in fractals this basically means a different way to calculate the same formula. So if I go to the normal, you know, this fractal looks like that, a pretty classic of a Mandelbrot. And if I go to the Julia mode, it's just a different way to calculate the formula. If you're interested, well, this means that in a normal way, basically for each point on the fractal surface, we use a different a little different formula, right? In the Julia mode, we use the same constant all over. So this constant here is the Julia constant. And this goes whenever you see a normal Julia slider, you also see a Julia constant, which is a great way to basically break up your fractal, right? For example, if I change this here, you can do very different things here, right? Of course, this looks a bit less detailed right now, and that's true because the resolution is pretty low, but we will get to this later on. And actually, I feel that I'm gonna close this one and I'm gonna move this one up so that I can actually see better what is happening on the node. I'm gonna just put those back to 0. I mean, all those parameters except the iteration and normal Julia are very fractal specific, so I'm not gonna explain every parameter of every fractal because I mean, some of those are just mathematical nonsense and then don't mean anything that's related to the actual like appearance of the fractal. Experiment with those, right? But in case of a Mandelbrot, you see the exponent basically tells how many sides the Mandelbrot has, right? If I put here 8, you see I have 7 sides to the Mandelbrot, and if I put here like 5, I have 4, basically 1 less all the time, right? And I'm going to put back the parameters as they were. Now the phase is basically for looping the fractal, and this was something that was highly requested under my Mandelbrot YouTube video, to have a parameter to loop the Mandelbrot, either the Mandelbrot or the Julia set of the Mandelbrot, right? This looks like that. And then we have a spikes option, which is again a fractal specific. You can have spikes here, which look pretty cool, and formula rotation, which is currently used here, right? Fractal specific, nothing to talk about here. The next things, however, are the same for all the fractals, and this is the scale, move around, rotate, and the ones down here as well, but we'll get to those later on. Now, the scale, move around, and rotate are basically for finding or moving the fractal to a location that you like. And you're asking, well, I can just move those with, you know, pressing G on the keyboard and moving this around, right? Well, that is true, but the fractal is calculated inside of a domain, right? This is actually not the real domain, but it's a good way to visualize this. So the fractal is, and it just happens to match currently. So for example, if I move this, right, you see only this part of the fractal is calculated. And this is defined by the domains down here, right? For example, if I move this down on the Z-axis, I can do this like that. And the scale, move around, and rotate are used to, for example, if you want to only view this part of the fractal, well, you should zoom up to this part. So how do we do this? Well, we just, first, of course, we scale. This has moved out of bounds. So I'm just gonna do my best to find this part by moving on the Z axis and now scaling again. And you see this is the part of the fractal. And just notice this is much more detailed than it was before. And that's because of the detail things down here, but we'll discuss those just in a minute. The next thing is rotation. So as you see, this is basically just for rotating the fractal. And as you see, this is rotating the formula, or actually like the internal fractal, not just, you can also rotate this like that. This is rotating the object, but this is rotating the fractal coordinate system so that, you know, for example, if you want this to be in a different calculated in a different way, you want to find a different location, then you can do this, right? But these are just like general moving inside of the bounds, these 3 controls. The next one is mesh boundary. So the fractals are calculated as an SDF, which means assigned distance function. What this means is I have a certain field of distance. Yes, I'm not using a graphics tablet right now, so this might look a bit ugly, but you understand what I mean, right? I have a certain distance field, right? And I can pick a certain surface here, which is called isosurface, I believe. And I can, for example, decide how big of a, let's say, sphere I want in this case. Now, fractals are also SDFs, so calculated like that mathematically. So I can select where do I want the mesh boundary to be, right? Do I want to use the one very much in the center, like very much close here, right? Or do I want to move out on the field, along the field, and use something different? For example, in our case, this brought up some cool tentacle-like things here, but this is also useful for solving detail issues. For example, when you have too many iterations and they bring up things like that, you might want to add a little bit of mesh boundary to mitigate this issue. But it's of course good to have just as much iterations as you actually need. And the next thing is minimum bounds and the maximum bounds. Now these are very self-explanatory, I believe, once you understand them. So the minimum bounds is just x, y, and z, x, y, and z. So what is the maximum length from the object origin that the fractal is still calculated, right? If I don't want to calculate this side of the fractal, well, then I have to remove the negative x part, right? So on the x, I want this to cut at 0, so this is at the center, right? This is basically just to cut away the parts of the fractal that you don't need at all, right? And it's a very clever way to optimize. So these are the bounds, and the resolution is on each axis, how many voxels do we calculate? As you see right now, we have much more detail along the y-axis and the z-axis, but on the x-axis things are like stretched out because we don't have much resolution on this axis. So in the optimization video, we'll look more at how do you understand those numbers more deeply. But basically more voxels means more resolution and also much more calculation time. So actually double the voxel amount means 8 times more calculation time. So keep that in mind, and in the optimization video we'll talk about how to approach this problem the best way. And this is basically the fractal, right? I'm going to delete this. I'm going to show you with one more fractal, just the parameters, something easier. For example, this Apollonian fractal. All right, I'm going to open up this one. And let's see what the parameters look like. This one has been optimized. As you know, as you see, there are some nodes here, but the fractal core is still this node group here, right? First, of course, you see, again, a fractal specific parameters, iterations, less iterations, less detail, right? This is how you can add detail. And squeeze is basically just a fractal specific parameter that squeezes the fractal together. And then there is formula scale. So for this fractal, this specific fractal, we have only 1, 2, 3 parameters, right? And then we have, of course, again, the same scale, move around and rotate, which is just covered, resolution, mesh boundary, and minimum bounds and maximum bounds, right? And the material in the end, I forgot to tell you about that. So this is the material of the fractal object itself. In the next video, we'll look at how to optimize the fractals and get the best speed and the best looks possible.